Welcome to the lecture series by MSB on main group elements. In my previous lecture, I was discussing about chalcogen halides. Let me continue from where I had stopped. Sulfur does not react directly with iodine, but in the presence of SbF5, a fluorine acceptor, it forms a cation of this type. So, this one is cationic, okay. This is essentially having S7I plus SB F6 minus. Saturated hydrocarbons are dehydrogenated when heated with sulfur, and further reaction with alkenes occurs. That means, when you do dehydrogenation of saturated hydrocarbons, alkenes are formed. These alkenes further react with sulfur, and application of this property comes in vulcanization of rubber, in which soft rubber is toughened by cross linking of the isoprene chains, making it suitable for use in, for example, tires. The reactions of sulfur with CO or cyanide yield COCS or NCS. Okay. While treatment with sulfides gives thiosulfates. For example, of course, the structure of this one is similar to CO2, and one can also write the thiocyanate structure, or one can also write another possible structure like this. This is thiocyanate, and sulfide gives thiosulfates. For example, Na2SO3 reacts with one equivalent of sulfur, so 1/8 of sulfur in aqueous medium at 373 Kelvin to give Na2S2O3. So, oxidation of S8 by ASF5 or SbF5 in liquid SO2 yields salts containing cations such as S42 plus, S82 plus, or even S192 plus. For example, in the reaction of S8 with ASF5 in liquid sulfur dioxide, okay. So, this is one such dication. 2 electron oxidation of S8 results in a change in ring conformation. The red colored S8 2 plus cation was originally reported as being blue, but the blue color is now known to arise from the presence of radical impurities such as S5 plus. So, it is essentially not blue, it should be red. The blue color originally noticed was essentially due to the presence of this radical impurity such as S5 plus. Okay. So, let me write the structures of those. So, this is S8, 2 electron oxidation leads to dicationic compound, dication. Here essentially one of the resonance structure if I write, so 2 sulfurs will have positive charge, and here it is very interesting to compare the bond parameters. This distance is 296 picometer, this distance is 286 picometer, and this distance is 204 picometer, and this distance is 206 picometer. Okay. So, this is one of the resonance structures of S8 2 plus. Similarly, let me write the structure of S19 2 plus. So, this is essentially if I start numbering, I can start numbering, I can start somewhere, it does not matter 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So, it is essentially S19 2 plus. Selenium also possesses several allotropes. Crystalline red monoclinic selenium exists in 3 forms, each containing SE8 rings with the crown conformation very similar to SE8, and elemental selenium can be prepared by treating selenium chloride with triphenyl phosphine selenide. For example, 4SeCl2, when it is treated with 4 equivalents of triphenyl phosphine selenide, it leads to the formation of SE8. Okay. In this case, if you substitute selenium with sulfur, one can make a series of mixed chalcogen compounds of this type. For example, Se N S8 minus N one can prepare where N equals 1 to 5. So, that means this method gives a scope for the preparation of mixed chalcogen rings. Tellurium has only one crystalline form, which is a silvery white metallic looking solid. Selenium and tellurium are less reactive, but are chemically very similar to sulfur. This is also true in the case of cations such as Se4 2 plus or tellurium 4 2 plus, Se8 2 plus and tellurium 8 2 plus. So, that means they are more or less similar to sulfur. So, these are all polychalcogen cations. You can see here, of course, when it comes to oxygen, it is only one monocationic O2 plus is known, and that too when it is reacted with fluorine, whereas in case of sulfur you can see S4 2 plus, Se8 2 plus up to S19 2 plus can be made. Similarly, in case of selenium one can make these species. In case of tellurium, tellurium 4 and tellurium 6 respectively in the +2 and +4 state are known, and this is for the tetrachalcogen dication species the structure, whereas this one I already showed you S and Se8 2 plus dications. The salt I was telling you about in case of selenium that can be readily made Se8 dicationic salt can be made very similar to the sulfur analog. For example, Se8 when it is treated with 3AsF5 in liquid sulfur dioxide, it forms Se8 dication through the fluorination of arsenium. Okay. So, the preparation of tellurium takes a slightly different method. Here in the preparation of tellurium analog, that is Te8 2 plus, recent methods use metal halides such as ReCl4 or WCl6 as oxidizing agents. Let me write one such reaction here. For example, rhenium tetrachloride when it is treated with tellurium in presence of tellurium tetrachloride, of course, this reaction has to be carried out in a sealed tube. It leads to the formation of Te8 dication. Okay. And preparation of Te6 4 plus involves the reaction of tellurium with arsenic pentafluoride, of course, in presence of AsF3. And if you look into the structure of Te8 2 plus, this structure is very similar to that of sulfur. Okay. But in case of tellurium 8, if you use tungsten hexachloride, the cation has the bicyclic structure. Okay, so this is Te8 2 plus, this is very similar to the sulfur and selenium analog, whereas in case of tellurium 6 4 plus, it has a trigonal prismatic structure. So, here just if you look into this is A and this is B, let me give the A, this tellurium bond distance is in the range of 266 to 269 picometer, whereas these bond distances are in the range of little longer, (306 to 315 picometer). So, this is your Te6 4 plus. Selenium and tellurium essentially consists of long spiral molecules with weak metallic interactions between adjacent chains, which break down into smaller rings and chains on melting. Polonium occurs naturally as a trace component of uranium over pitch blende, but is made artificially by the irradiation of 209 bismuth with neutrons. Which eventually it gives 210 bismuth, that eventually emits beta to give 209 polonium. So, this is the artificial method of preparation of polonium, isotope 209. Now, let us look into the hydrides of group 16 elements. The most important hydride of any element is that of oxygen, namely water or oxane. Water is the only group 16 hydride that is not at all poisonous. Its melting and boiling points are known, 0 degree centigrade and 100 degree centigrade respectively. Its melting and boiling points are very high compared to compounds of similar molecular mass and the analogous molecules in group 16. This is essentially because of the strong hydrogen bonding that we learned when we were discussing about the chemistry of hydrogen in my earlier lectures. Let me not go into the details. The high boiling point is due to extensive hydrogen bonding between hydrogen and highly electronegative oxygen. Oxygen also forms hydrogen peroxide, that is H2O2. A deuterium label in heavy water is indicated by writing 2H2 water, or simply, so this indicates it is heavy water or D2O, and similarly for other labeled compounds. Compounds in which hydrogen atoms have been replaced by D are used for a variety of purposes. Example as solvents in NMR spectroscopy. The difference in boiling points indicates that intermolecular hydrogen bonding is stronger in D2O than in H2O. Of course, the boiling point of D2O is 101 degree centigrade, whereas that of water is 100 degree centigrade. Only 1 degree difference is there. The major industrial use of D2O is as a moderator in nuclear reactors. Deuterium has a much lower cross section for neutron capture than hydrogen, and D2O is a suitable material for reducing the energies of fast neutrons produced in a typical nuclear fission reaction. So, I have listed some of the properties of water and heavy water here. Of course, boiling point melting point little difference is there, and the density also little bit difference is there, and maximum density is 0.99995 in case of water, whereas in case of D2 it is 1.10. Relative permittivity also not much major difference is there. And hydrogen peroxide, about hydrogen peroxide also I had already discussed its method of preparation while discussing the chemistry of hydrogen. H2O2 is the most well known peroxide which adopts gauge structure both in the gas phase and in the solid state owing to the repulsion of the lone pairs on the oxygen atoms. Hydrogen peroxide undergoes self ionization to water, but to a greater extent when compared to that of water. For example, 2H2O2 okay. So, here if you look into the equilibrium constant, this is 1.5 into 10 to the power of minus 12. In case of water, so in case of water equilibrium constant is 10 to the power of minus 14. Okay, I will be showing. So, this is how the structure of hydrogen peroxide looks like. So, hydrogen peroxide is stable towards decomposition into hydrogen and oxygen due to the large negative enthalpy of formation. You can see delta FH for hydrogen peroxide is minus 187.8 kilojoules per mole. As a result, okay, it does not decompose into oxygen and hydrogen. Instead, what it does is it decomposes to water and oxygen. So, industrial method of preparation of hydrogen peroxide involves the anthraquinone auto oxidation process. Anthraquinol dissolved in an organic solvent is oxidized to anthraquinone and hydrogen peroxide is formed. The hydrogen peroxide is recovered by extracting the organic solution with water. The anthraquinone is then reduced back to the anthraquinol using hydrogen and a palladium complex or palladium metal as catalyst. This process repeated many times giving a catalytic cycle. You can see here the auto oxidation of anthraquinol to form anthraquinone, and H2O2 is liberated, and H2O2 is from organic phase to aqueous phase, and then anthraquinone is treated with hydrogen using palladium catalyst to regenerate anthraquinol to start the second cycle. And in laboratory, small scale preparation of hydrogen peroxide involves the reaction of barium peroxide with sulfuric acid that leads to the formation of barium sulfate and H2O2. Hydrogen peroxide is a very powerful oxidizing agent. It oxidizes iodide to iodine, SO2 to H2SO4 in alkaline solution, and chromium 3 compounds to chromium 6 compounds. In fact, powerful oxidants such as MnO4 minus and Cl2 will oxidize H2O2, and in alkaline solution H2O2 is a good reducing agent. Let me write a couple of these equations for you. So, this indicates the reducing nature of H2O2. Hydrogen sulfide is more toxic than hydrogen cyanide, but because H2S has a very characteristic odor of rotten eggs, it can be easily recognized. So, in the laboratory, H2S was historically prepared by reaction of FES in a Kipps apparatus. That method involves the treatment of FES with aqueous HCl Okay. Hydrolysis of calcium or barium sulfides also produces pure hydrogen sulfide. For example, if you take calcium sulfide and treat this one with water, it gives H2S and calcium hydroxide. In aqueous solution, the hydrides behave as weak acids. A qualitative test for H2S is its reaction with aqueous lead acetate forming block precipitate. That is essentially due to the formation of PBS. For example, H2S plus PB lead acetate gives lead sulfide plus acetic acid. So, this is block precipitate. Hydrogen selenide may be prepared by the reaction of Al2SE3, and a similar reaction can be used to make tellurium hydride as well. Let me give the preparation of hydrogen selenide or selenium hydride. The enthalpies of formation of H2S, H2SE and H2TE indicate that the sulfide can be prepared by direct combination of H2 and sulfur. It is more stable with respect to the decomposition into its elements than H2SE or H2 tellurium, that means selenium or tellurium hydrides. Let me stop at this stage. In my next lecture, I will be continuing the chemistry of group 16 elements. Until then, have a pleasant reading of inorganic chemistry. Thank you.